Welcome to another episode of Talon Tech Teaches. Today's problem: achieving linear motion. Linear motion is used in most robotics competitions, with this season being a bit of an outlier, having many teams placed on the back burner. But because it is used in so many robotics use cases, it's what we'll be focusing on today. Here we have some rough sketches of 4 different types of linear motion. Starting on this left side, linear slides, very common. We have screw linear actuators, lead screw, screw-based linear actuators, box tubes, and finally rack and pinion systems. Now to go into a little bit more detail.
The most common way to achieve this linear motion is probably linear slides. Some common examples are the GoBuilda Viper slides and Mizumi drawer slides. GoBuilda uses belts now to drive their slides, but many teams prefer string slides because they can be packaged much more easily and can allow for the string to be routed many different ways on the robot, allowing greater variability in design. GoBuilda slides have also been criticized for their weight, but they still provide strong, reliable slides. Mizumis are a much lighter alternative, also smaller, but they need to be modified with bearings and 3D printed mounts for use. This can sometimes present a bigger challenge than some teams are willing to face, but here's a video of my team's robot from last year using our custom strung Mizumis for linear extension. Although rigging slides with strings and belts is very common for vertical extension, using linkages is also very popular for horizontal extension. Right here, you can see we have a fully retracted slide system right here, with this black wheel being the pulley, these small black circles being our bearings, and this red string acting as our string. So as you can see, this is the most complicated path it can take, or the longest path that the string can take. It goes over the first pulley, now at the very top of the first slide, because this is your base kind of normal thing, not including any stroke length. And then you go on your next slide, and wraps around these bottom one across the top, and then when you get to your final stage, you tie it at the bottom, because that's going to be the bottom of the topmost layer. If we drag over though, we have this as our fully extended stage. Let's shrink that. Okay, so this is once the pulley wraps up, it tightens the string to its tightest possible configuration. So this one takes as much room as possible, the one on the left, but the one on the right uses as little string as possible, with the rest being wrapped up in the spool. So it goes over the first one, and then it's much easier for the string to be right next to the top of the first slide, as that's a much shorter path than going from the top of the first slide to the bottom of the second. So that way, those two slides are right next to each other practically. And then it goes up, and then it pulls the bottom of the third slide up to the top of the second, as you can see here. Another way teams can achieve this motion is with a screw-based design. A very popular version of this is seen with the GoBuilda linear actuator kit. This design can also be seen in some 3D printers like the Creality K2, which uses a screw-based actuator to level its beds. My team actually used this GoBuilda linear actuator during the center stage season to climb. One thing to note though is that because of a large reduction created by the lead screw, this actuator is best used for a problem that involves heavy loads. This solution for linear motion would not be used for any kind of cycling or repeated motions like into the deep, constantly extending and retracting up to the basket or to the high bar. This is not going to be the best use case for a lead-based screw or a lead screw design. This would be something like climbing, level 3 climb, or like center stage, climbing those trusses. As we can see over here, we have our motor on the left, our lead screw, and our end effector. I hope you guys are liking this MS Paint drawing. As the motor spins, clockwise or counterclockwise, it causes this lead screw to move, and as this is restrained from rotating, it has no choice but to slide up and down based on the rotation of this motor, this lead screw. Box tubes are another way to achieve this motion, incorporating nested tubes that use string and pulleys to extend. I first learned about this type of slide through KookieBots in center stage, but since then they've been popularized with Offset Robotics selling their very own, and Theseus recently using them to earn their base points. This mechanism differs from the usual slide extension, as they are rigid squares instead of thin drawer slides. This means only one set of box tubes is needed to eliminate backlash when there would usually be 2 sets of drawer slides to achieve the same effect. The final way to achieve linear motion we will be talking about is a rack and pinion design. In a rack and pinion setup, there is the pinion gear which is powered and receives the torque that converts the rack into linear motion. By running the gear, the rack meshes with the pinion and is propelled forward. This design can sometimes be used for claws and climbs and is one of the easier ways to achieve linear motion without extra headache. It is important to note that the rack should always be supported so that it will not slip from the gear, which can sometimes be hard with a low gear module.